started, a couple announcements. First up, just a reminder, of course, that your next homework assignment is due on Thursday. So homework assignment number 3, I guess, is due on Thursday. There's going to be another lab assigned on Thursday. So we'll talk about that lab on Thursday, but I'll give you kind of a spoiler right now. What we're going to do today, very first thing today, is going to be directly applicable to that lab. So you picked a great day to come to class because it's going to help you with the next lab assignments. We'll talk about that a lot more on Thursday. The videos for the next couple sections are actually completed. I just forgot to post them. I realized that right as I was walking out the door to class that I forgot to post them. So the videos for the next section are ready. I will post those as soon as possible. I'm sorry about that. That's totally my bad. They will be posted by the end of the day today. No problem. I'm trying to think of what else. The exam's coming up in about 2 weeks. We'll talk about that in a little bit. Question? It'll be due probably the class session before the exam. So 2 weeks from today, I think is when it'll be. So you'll have over a week to knock it out. And it'll be a great review for the exam as well. Yep. The exam is 2 weeks from Thursday, so the lab will be due 2 weeks from today before the exam. And we'll have another review session for the exam. We'll talk about all that fun stuff when we get to it. The side book, was that due today as well? That was due today, wasn't it? I don't remember when that was due.
It's due Thursday.
It's due Thursday. Okay, cool. Yeah, it's due Thursday. Thanks. So the chapter 3 of the Xi book is due on Thursday. So make sure you go back and take a look at that. If you haven't been keeping up with it, now's a good time to go back and pick up those sections. Any other questions about logistical stuff before we take a look at some VHDL? All right, so there was a problem last Thursday that I really wanted to get to. It was more of a demo, actually, that I really wanted to get to. We ran out of time last Thursday, but it is so important. It's going to be so useful for you when you're working on the next lab that I want to spend time on it today. I realize today's topic is supposed to be timing, and I'm hoping that there will be some time at the end of class to talk about those kinds of timing problems. If not, we'll definitely spend some time talking about that on Thursday because that is a very important topic as well. But this is just so important. So I want to take the first part of class and work through this finite state machine demo. So this is the garage door finite state machine. We've been watching the videos. We've seen this before. We've actually talked about this in class before, right? This is a finite state machine that we are hopefully familiar with for the most part by this point in the class. And what I want to do first thing today is just go through how we would code this up in VHDL. So lab 3, which is about to be posted, is going to ask you to do the very same thing. It's going to ask you to code up a finite state machine in VHDL. So let's go through this and talk about what that actually looks like. Before we do, there's one very important thing that we actually need to discuss as a group. There's one very important piece that's missing from this finite state machine. Does anybody see what it is? I might have mentioned this earlier, actually. Yeah. Oh, I saw 2 people. Anyway, where do we start? Yeah. So where do we start? Where does this thing start? It's missing. It's not included, right? So any takers as to anybody want to offer a suggestion on where we should start? I'm not sure that it matters a whole lot, but yeah.
I would guess closed.
Closed. Yeah. Okay. We can do closed if you want. Sure. Or open. I don't care. Like. I don't think it really matters. We just need to choose one. So we'll choose closed. So closed is going to be our initial state. That's going to be important for us when we're going through the VHDL in just a second. So I've already gotten us started with some VHDL. In fact, I've already defined the entity for this. All right. The entity is just the inputs and outputs, but you'll notice there's a few extras in there as well, right? The clock is going to be important, because we are now talking about synchronous circuits. Last Thursday we went through a lot of examples about what VHDL looks like for synchronous things. So the clock's going to matter. We also have an input for reset. Right? So it's pretty common practice to include a way to bring us back to our initial starting configuration. Let's say we screw up and we're lost. We don't know what state we're currently in for whatever reason. I want a way to reset and go back to the beginning, so that I can work my way through and figure out where I am. Everything else is directly from the finite state machine, right? I've got 4 inputs, it looks like. the open close button, the obstruction sensor, whether I'm at the top, whether I'm at the bottom, and then two outputs. One telling the door to go up, one telling the door to go down. This is all directly from our finite state machine. Right? So our next task then is to define the behavior. You'll notice that's all I've spotted you. This is it. This is all the freebies you're going to get from me. The rest has to come from you guys. So what should I do first? What do I need in order to code up this finite state machine? Does anybody remember from the video some tools that might help us? Yeah. Great. Perfect. I need to define my states. I need to define a type to represent my states. So that's going to go inside. I'm going to use my cheat sheet because it is a fair amount of code here. And I want to make sure I get this right. So I'm going to define a type for my states. And the way that that looks is something like this. Right? Type, and then this is just the name. So this could be anything. I'm going to call it state type if we're going to use this to represent our states. But I could have called it whatever I wanted, right? And then I have to specify what I want the acceptable values for this type to be. What are my acceptable values? In the case of a finite state machine, those are going to be the names of our states. So it's pretty simple. I'll just put the names of my states in here. So I've got opened, I've got closed, I've got opening, closing, pause up, and pause down. And that's it. Semicolon. Let me scoot some of this stuff out of the way if I can, so that we can see it all. Right? So all this is doing is defining a type for my states and then listing the acceptable values for this, which are just the states that I can be in. What is ultimately going to become of this information? What is Xilinx going to do with this info eventually for us? So, yeah. So we are going to talk about lookup tables. Absolutely, lookup tables are used for logic, right? Is there any logic involved here? Not necessarily, right? But consider everything I write in VHDL has to become an equivalent part of a circuit, right? Everything I write in VHDL becomes a circuit. So what part of the circuit creation process is this option for us? How are states represented in our circuits? I'm sorry? Bits, right? So how do I determine what bits represent what state? What's that called? I have to encode them. I have to encode my states. So this is performing the encoding for me. In fact, it makes it really easy. I don't have to decide what kind of encoding I want. This just tells Xilinx to figure it out. Is it using one-hot encoding? Is it using binary encoding? It's actually probably going to try them both and choose the best one. And best being the one that it can accomplish with the fewest amount of flip-flops, fewest amount of gates, right, at the fastest possible. So this takes care of the encoding process for us. It just takes it out of our hands. We don't have to worry about it anymore. It's done. It's done. So that's a nice thing. That's convenient for us, right? That's a good thing to have. Okay, great. The next thing that we need to do is what? Any idea? What are some pieces that we expect to see in this VHDL? Yeah? We do need to define the transitions for each state. That's pretty much the entire bulk of what needs to come next. So where am I going to find those transitions? What structures am I going to need for those transitions? What do I want to use? When does the transition take place? Right? So what happens when we transition from one state to the next? It determines the state that we're transitioning to, right? And then where's that state stored again? Where do I store what state I'm currently in my circuit? In the flip-flops. And when are flip-flops active? On the rising edge of the clock. So how do I specify that in code? What do I need to say? If rising underscore edge, so that's certainly part of it, right? We're going to need that, so I'll write that down. Am I missing anything? Does this sit well with everybody? I need a process. Right? Yes, that would have come back to us eventually. The question was, don't we also need a signal for the state? The answer is yes, absolutely. We need to create a signal for the state that we currently are in, and it looks something like this. I'm going to define a signal called state. What type do I want this signal called state to have? I want it to be state. Thank you for pointing that out. We also need that process. That was the piece I was really looking for. We need this process. What goes inside the parentheses? The clock, right? What does that mean? What does it mean to put clock in there? It's a sensitivity list. It indicates that it's a synchronous process. This will only execute whenever the clock changes, right? It will only execute when the value of the clock changes. Fantastic. Oops, I'm also just missing a little syntax here. I need that begin. That would have come back to hurt us later. All right, let me just make sure that my indentation looks good. All right, got process clock. I also need a begin here. Just clean up the syntax a little bit. Okay. So here we are. This is great. We're in great shape. We've defined what our states are. We've created a signal to hold our state, right? Created a signal to hold what our state should be. Excuse me. Now let's define our reset condition first. Remember, we stated that a reset condition is useful to bring us back to our initial starting point. We said that our initial starting point is going to be the closed state. That's where we initially want to start. So how do I say that? How do I detect that I want to reset and then put myself back into my initial starting state? Yeah.
Add reset to the sensitivity list and then
if, okay, so let me break that down. If reset equals 1, oops, like this, then we can say state is set to, what we say, closed, I guess. It could be anything, right? It could be anything. Fine. Okay. So what was the other thing you said? You said add something.
well, I was thinking if reset changes and not on the rising edge to reset.
That's a good question. If reset changes and I'm not on the rising edge of the clock, do I actually reset? What do you guys think? Do they have any takers? Yeah.
It's all synchronous.
It's all synchronous, so no, we don't. We only ever change state on the rising clock. Every single state change is dependent on the clock. Always, 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 always on the clock. So, you know, including reset inside your sensitivity list, I don't think would have broken anything. Right? It wouldn't have changed the overall functionality of our circuit, but it's also not necessary. It's also not required. So far, clock is the only thing that's absolutely, positively required. Okay, so that handles our reset logic. And now, in the else statement here, we can start to specify the rest of our logic for our finite state machine. Basically, all of our transitions, right? All of our transitions need to go here. All of them. So what structure am I going to use to specify transitions for me? Yeah. Case when is a great candidate. I like that suggestion a lot. So let's do it. This is going to be, you know, somewhat tedious, I suppose, because it's going to start to look a little bit repetitive. But this is how it works, right? So I'll say case state is, and then I just have a whole bunch of when statements, one for each state. So I'll have one for when opened, for example, arrow. So at this point in time, I want to start specifying transitions. What kind of finite state machine was this? Got two choices, right? What kind of finite state machine? It was a Moore machine, right? So actually, it doesn't really matter what kind it is for my next question. How do I determine what my next state is? What do I need to determine that information? My inputs. That's all that really matters. My inputs and my current state. So my current state is specified by this, right? This is my current state. Where am I right now? The only other thing that I need are my inputs. So if I go back to my finite state machine, I look at this opened state right here, I see that if the obstruction is true or open close is false and the obstruction is false, then I'm going to remain in my current state. Right? So that's one transition. And you could actually code it up very similarly to what I just said. I just said if this and this, or if that and that, then state is equal to next state. Actually, these self loops are pretty easy. You really don't necessarily need to include them, right? Because if I just don't change my current state at all, then I'll remain in the current state that I'm in. So really, I'm not going to bother coding up these self loops. It's faster to just omit them. Again, not going to hurt you if you do code them up. It's just a little extra typing that you have to do. So I want to focus on this one instead. This is the only other transition out of opened that I have. So that says if open close is true and obstruction is false, then the next state should be closing. So let's code that up. If open, what did I call that? Open close, where am I here? Yeah, open close equals 1, right? If open close is true and obstruction equals 0, then state should be closing, right? That's the only transition that I have to worry about. Like I said, we don't have to code up self loops. You can, but we don't have to, so I'm not going to. This is the only transition that's not a self loop that I need to worry about. So I'm done with this state. Question?
Your first assignment is that you didn't use parentheses.
Oh, quotes. Thank you very much. You're absolutely right. I don't need the quotes. That was a habit from whenever I type text in a variable assignment, it's just habit to put it in quotes. That's what most languages do. Thank you for pointing that out. Any other questions about what we've done so far? So the rest of this should follow very nicely, right? In fact, you know, how many states were there? 6. So it's just going to be, you know, 5 more of these when statements. Why don't you go ahead and talk to your neighbors, take a few minutes, see if you can figure out what the rest of these should look like. I'll start typing them in up here, right? Or you can sit there and watch me if you want, but that's pretty boring. I think it'd be better for you to try and figure it out for yourself. Ellie can come around if you have any questions. And then we'll regroup and finish this up in just a little bit. Okay, so let's take a look at what we have. Right? You see I've got one when clause for each state, and I just define all of my different transitions inside of particular when clauses. If you didn't get through all of them, that's fine. I do intend to post this code on Piazza after class today, so don't worry about it too much if you got stuck or if you didn't finish. I just didn't want to spend the entire class period going over the same transitions over and over again, so I just coded it up very quickly. What else do we need? So I've got my transitions, right? Got my state transitions. What else am I missing? Yeah.
The output.
The output assignments. Where should those go? Yeah.
In your current case one.
Say that one more time.
In your current case one state.
In my current case when state. So inside this case when statement, is that what you're saying?
Yeah.
They should go inside here. So what would that imply then? So they would go inside of each individual when class, or
yeah.
Okay. So just to remind ourselves again, we're working with a floor machine, which means the outputs are dependent on what? Just the current state. So that actually would work. I could stick the outputs directly inside of each individual clause, each individual when clause if I wanted to, right? Sure. So what are my outputs? My outputs are go up when I'm in opening and go down when I'm in closing. So if I wanted to do that, then I could say, oh, where is it? Here's opening, right? So I would say go up is set to 1. Now, the issue here is I set go up to be 1 in this particular case. It should be 0 in all the other cases. So I physically have to say go up is 0 in every single other condition, right? Which is not a bad thing. It's just a lot of typing. Is there a way that I could maybe reduce the amount of typing that I need to do? I know you guys have ideas. Can I get somebody different? I believe you. Yeah. Sure. Exactly. So I could say that, where would that go? Maybe here, I guess, inside the else. Go up, set to 0. Sure, I like that a lot. Because the way that a process works, right, is that it operates sequentially, but it only actually changes the values when? At the very end, right? So if I overwrite, if I set something equal to 0 and later on I set it to be equal to 1, will I ever be able to see that value is set to 0? No, I won't. I'll only ever see the final assignment that takes place. I'll only ever see the one that takes place. That works. That works. Yeah. Any other ideas? There's actually lots of other ones. Nobody's actually hit the way that I would have done it. Yeah.
To another case when statement and use the default to assign.
To another case when statement.
Your state use the default to assign.
Oh, I see. So yeah. So when others, right?
Yeah.
So if I'm in opening, then set it that way. If I'm in closing, set it that way. Otherwise, set them both to 0. Perfect. Yeah, that would work. Here's a question for you: Are the outputs dependent on the clock? It's a tricky question a little bit. What are the outputs dependent on in the Moore machine? They're dependent on the current state, and the current state definitely depends on the clock, right? So you could make the argument that the outputs are dependent on the clock by association to the states, right? But the outputs are not directly dependent on the clock. Do I have to include them in the process at all? I don't. It's not necessary. So I'm not trying to say that what was suggested is wrong. It's not wrong at all. It's very correct and certainly would work. You should go ahead and do it. You would not ever be marked off for that for any reason whatsoever. But just to offer you some alternatives, right? I could also set those outside of the process entirely if I wanted to. I could say something like this. Right? That takes care of one of my outputs outside of the process. It treats it as though it's asynchronous in a sense. In fact, the reason why I prefer this method myself is that if I were to convert this to a Mealy machine, right? If I were to convert this into a Mealy machine at some point, that means my outputs are no longer dependent on just the state. They're dependent on the state and what? the inputs, which means they can't really go in the process anymore, or they could, but you'd have to change the process quite significantly, right? They truly would become asynchronous outputs at that point, and so keeping them outside of the synchronous process, I think, is more appropriate in that case. Again, not necessarily better, just, I think, from an organizational standpoint, good practice. Yeah, questions?
So now that go up is assigned outside the process.
Mm-hmm.
When does that assignment take place? At the same exact time? Is it asynchronous to the process? Is that how that works, or is it synchronous?
That's a great question. So the process, right, does all of its assignments at the very end. And you can think of any other things that I have outside of this process happening at the exact same time as all the other stuff. If the process doesn't fire, then these are still going to be operating, but they wouldn't have any effect in this case because nothing's going to change unless the process executes. So I know that's a little bit complicated, right? Everything eventually happens simultaneously. Everything eventually happens in parallel. The way that we get around that restriction, since it's confusing for people to think in parallel, is to use a process. But even that process is taken in parallel with all of the other non-process stuff.
So that assignment will take place before the state change.
It would take place at exactly the same time as the state change. So, you know, whatever the state happens to be, right? If the state is closed, then this would be 0. But as soon as the state changes to opening, this would immediately switch over to being true. And if it changed to something else, this would immediately switch back. It's not going to wait for the clock. It's not going to wait for anything. It's just going to happen right away, right? If I wanted to make it wait for the clock specifically, then I could put it in the process. In this case, it wouldn't hurt anything, right? Because this is dependent on the state, which already depends on the clock. Which is why the previous solutions offered were not wrong at all. In a Mealy machine, they would be problematic, but in a Moore machine, there's no problem. At all. So that's an important distinction to make. This way, I think, is perhaps a little bit less typing than some of the options that were offered. Let me just finish this up really quickly. You know, I really like this, regardless of how well it works or doesn't work. I mean, all of the options offered work, right? But regardless of that, I like this more because it keeps things separate. It keeps my output logic separate from my next state logic. I like that a lot. I can now change the transitions without having any effect on the output, or I can change the output without having any effect on the transitions, vice versa. That's a good thing to me from a design perspective. Okay. Any other questions? Anything we're missing? Anything you think that we need that we don't have? Yeah. Yeah, go ahead. We did the reset logic, right? So here we said if reset is 1, then state is closed. Yes, and that's good practice if I have the reset capability available. And this is regardless of the component, whether it's a finite state machine, whether it's any synchronous component whatsoever, it does not matter. It assumes that you will give it a reset period at the very beginning. So it's good practice. So in your test bench, the first thing that you would do before you do any tests is you set the reset signal high on everything that has a reset signal, and then do your test after that. Yeah. Great question. Any other questions before we move on? Right? So I actually brought the FPGA with me today, right? So that I could actually deploy this, and I want to give you a chance, you know, to kind of play around with that later on if you would like to. But I'd also like to take a moment to talk about how we can connect our modules to the stuff that's required for the FPGA. I had you do that in the last lab, right? But it was all sort of given to you. I basically said, here's the stuff that you need, and then you did a couple little changes, and then it was good to go. In the next lab, I'm still gonna give you a lot of stuff to use to connect to the FPGA, but I'm gonna ask you to do a little bit more of the work to get it ready for the FPGA. So let's take a look at how we can actually hook this up to work with the FPGA itself. So in every project that you want to deploy to hardware, deploy to an FPGA, you need a topmost module. So this is going to be the highest possible level, right? It's not contained within anything else. It is the topmost layer of your circuit. And typically that topmost module is going to be a bunch of component declarations So you'll see that in this module here, right, I've got a whole bunch of components in here. And some of these components you'll recognize from the previous lab. I never really talked to you about what these components are or what they do. Now's a good time, though, to discuss some of what these things are and what they're used for. So binary in mod, well, first off, we see the component for the opener. That's the finite state machine that we just created, right? That's us. So we know what this is. We don't have to worry about that so much. Binary in mod is what's in charge of processing all the possible forms of input on the FPGA. So on the FPGA, we've got switches, we've got a knob that we can turn. You can actually press the knob in, kind of like you can press a joystick in on a Xbox controller. We've got buttons. I think that's about it. Knobs, buttons, switches. Yeah, I think that's about it. Right. So what this binary input module is in charge of doing is detecting when that knob is rotated and updating a value accordingly. The way that it works, you saw this on the last lab. When I turn the knob clockwise, it counts up. When I turn the knob counterclockwise, it takes a value and counts down, right? There's logic involved with that. That's just not automatic. It's part of the FPGA. So if you go and look at the binary in mod code, you'll see that there's a further component called a knob interface that detects rotations of the knob and then increments the counter, essentially, when the knob is rotated, right? So that's part of the input interface. There's other stuff for the buttons. When you push a button down, there's metal contacts in there that allow current to pass through. But when you actually push that button down, those contacts don't come together and stay together. They actually bounce, right? They kind of jiggle a little bit. They bounce against each other a lot. So in actuality, when you push that button down once from our perspective, from the circuit perspective, it seems like that button's been pushed a whole bunch of times because it takes those contacts a little bit of time before they actually match together, if that makes sense. So another important part of this binary in mod component is a debouncer. It basically says, okay, I see that the button contacts touch one another. I'm going to ignore any jostling that happens for a set period of time after that first initial contact. We might take a look at that debouncer circuit actually in a little bit more detail in future classes. But for now, you should just know that it's there. That's all that I'm particularly concerned about. So I think that's basically it. And then what it does, what the binary in mod circuit does primarily, is it gives us these outputs, right? D button is the debounce button presses. So if I see D button 0 go high, that means button 0 is pressed. Okay. Pulse is also actually related to the buttons. Again, debounce buttons. It's slightly different. We'll talk about that when we talk about debouncing buttons in the future class. In bits is the value from the knob. So when I turn, right, that value counts up. That's actually in bits. That's what you're changing when you turn the knob. So in bits is what's counting up, counting down based on how you rotate the knob, right? Okay, and then we have binary out mod, which is in charge of all the different ways we can output stuff on the FPGA. That includes the lights, the LEDs, as well as the screen itself, the LCD screen, which has 2 rows of numbers. You saw that when you demoed on the previous lab. Right? So it takes values from a signal and turns those into actual numbers that are displayed on the screen. We're going to actually talk about how to do that in future labs, probably, as well as the LCD stuff. Right? Those are the big components to be concerned about. And then down here at the bottom, you can see what I want to do is use the knob to select a number that represents my inputs and outputs. Right? It's a binary value. We're only looking at the last 4 bits because I only have 4 inputs. Right? You see the 4 inputs here: open, close, obstruction, at top, and at bottom. Those are the only 4 inputs that I have. So I'm going to use the knob to select what I want those 4 inputs to be. They're all either 0 or 1. But there's a problem. The problem is that the clock speed of this FPGA is going really, really, really fast. Really, really, really fast. So if I just implemented this finite state machine on the FPGA and told it to go and started turning the knob, the transitions would happen so fast that I wouldn't even be able to see anything happen at all. It'd be too fast for me as a human to actually pay attention to. So the way that we get around this is that we tie it to one of the buttons. In this case, I'm using pulse 2, which is button 2. It basically means I'm only going to read this input when button 2 is pressed. Does that make sense? So I've now tied the inputs to a button. In other words, so that we can actually slow things down a little bit. And then I've got out bits. I guess I didn't explain what out bits were. Out bits are where is out bits fed into or coming out of? Top row, bottom row. Where are you, out bits? Oh, out bits is actually going to be the output of our finite state machine. You see here that I've connected out bits 1 to go up and outputs 0 to go down. We haven't seen this other syntax yet, but basically what we've said is we say position 0 of the array will be go down, position 1 of the array will be go up, and everything else in the array will be nothing. And then finally, we instantiate all of our components and connect everything together to the result. So here is our opener, right? Our garage door opener. You see that the reset signal is hooked up to button number 1, so that will reset us. Everything else is hooked up to the signals that we defined for that purpose. I will also post this online as well so that you can use it to help you with the next lab. Because I am going to ask you to do some of this stuff on the next lab. Are there any questions right now? I know I kind of hand-waved over some pieces with the promise that we will come back to it later, but are there any questions that I can answer for you right now? All right, fantastic. So then the last thing to do, and I'll do this while you guys are working on some more practice problems, is deploy to the FPGA. I actually have this ready to, I brought the FPGA for a reason. It will actually deploy. You can actually come down here at some point later on in the class and play around with it if you want, or stick around after class and play around with it if you want. But right now, I would like to maybe move on to some timing questions. Before I do, are there any questions at all about what we just did? Any questions about the VHDL stuff? Okay, cool. Let's take a look at some timing questions then. A few quick review questions, and then we'll try some more complicated problems in a little bit. What causes delay in our circuits? Tell me. Delay is everywhere, right? Why is it everywhere? What happens? Yeah. Gates cause delay, but more specifically, yeah. I mean, gates have delay. Everything does. Why is that? Where does the gate delay come from? Yeah. Transistors. Can you be more specific? Yeah. There are capacitors in our transistors. They aren't actually. We don't want them to be capacitors, right? That's not our desired operation for our transistors, but they're there. It's parasitic capacitance is what we call it. It's unintended capacitance. It's due actually, this goes way back to the beginning of the course, it's due actually to the junctures between the N-type and the P-type substrate in the transistors that causes that parasitic capacitance. But it exists in all kinds of components as well, not just transistors, but all kinds of stuff. So that's what causes the delay. The delay itself is caused because we have this inherent capacitance in our components. And that means when a signal changes from low to high, for example, it's actually charging that capacitor. When it changes from high to low, that capacitor has to then discharge, which does not happen instantaneously. It takes a little bit of time. What is setup time? What's the definition of setup time? Yeah, go ahead.
Time of the input must be high.
Not just high, but the time that is.
That must be constant.
Yeah, exactly. Yeah. The time that, so if I have a flip-flop, a D flip-flop, for example, and I want to give you an input, whatever that input is, high or low, I have to hold that input constant for a certain amount of time before the rising edge of the clock. If I don't hold it constant during that particular time, that's called the setup time, then I run the risk of instability. What exactly causes that? Why is that even a thing that exists? It seems really inconvenient, right? We know based off of our conversation that it's probably based on delay of some sort. Can you get a little bit more specific than that? Yeah. Exactly. So if we recall D flip-flop, what's actually inside of that D flip-flop? If I peel off the top and I look inside, what's inside of D flip-flop? 2 D latches, right? So I've got 2 D latches hooked up with one another. I don't care about the inputs and outputs right now. That doesn't matter to me for this particular exercise. But here's our input, right, coming in to the first D latch, and it's going through the second D latch. So setup time is due to the fact that this input is going to take a little bit of time to propagate through to this output. It's going to take some time for it to get there. So if we change it and it doesn't make it through before that rising edge of the clock period hits, then we don't necessarily know what this is going to be. It could be high, it could be low, it could be in the process of moving from high to low, which is probably the worst case scenario, right? Somewhere in between. That's going to cause metastability. That's going to cause a state where we don't know what this value is. That's setup time. It's due to this guy right here. What's hold time? Yeah. Yep, exactly. Hold time is after the rising edge of the clock. Setup time is before, hold time is after. So why does hold time exist? What's the reasoning for that? Yeah.
It takes a little bit for that first D latch to say.
It takes a little bit of time for this first D latch to switch from set or reset into the hold state, right? So you might be tempted to guess this, right? You might be tempted to say, oh, well, if setup time is due this latch, then hold time is due this latch. That's actually not it. It's actually more due to the fact of the clock. It takes the clock a little bit of time to propagate through this latch and change it from being in a state where I can change the value to being in a state where I cannot change the value, to where I'm storing something. So the hold time is a reflection of that fact. How do I go from a state where I can change the value to a state where I can't, where I need to hold that value? So hold time is basically propagation time for the clock through the first D latch. So this first D latch is what's causing us all the problems, right? Not necessarily, but most of the problems. Yeah. Okay. How do I determine the clock speed of a circuit? What am I looking for? I give you a circuit and I say, I want this circuit to go as fast as possible. Can I just set the clock speed to be, 0.000000001 picoseconds and call it a day? No, I can't, right? What do I have to do? Yeah.
Basically, as slow as possible.
So that's a good starting point. I need to find the slowest possible time through one route of the circuit. So what do we mean specifically by a route? What's at the beginning of the route? What's at the end of the route? What actually matters? Yeah. The beginning is an input that's based on the clock. So what are the things that are based on the clock in our circuit? Flip-flops. So the beginning of that route is a flip-flop. What's at the end of that route? Another flip-flop. So I'm looking for the longest possible route between 2 flip-flops. Right? So I have however many flip-flops in my circuit. Here's my D flip-flop, right? And I've got another D flip-flop over here, right? And I could have lots of these things in my circuit. I could have dozens, hundreds, thousands of D flip-flops, right? I'm looking for the one with the longest possible path, the largest amount of stuff in between, right? The longest delay from here to here. That's what's going to dictate my clock speed. What's this called, this longest path? We have a name for it. I heard somebody say it, critical path, right? We're looking for the critical path, the path with the most delay. One thing to be careful of, right? We're looking for the path with the longest delay. Be careful of this. I could have this path that goes all the way out here and comes back into the same flip-flop that it originated from. That counts. That counts. A flip-flop to itself counts. A flip-flop begins the route, it also ends the route. So this could be a critical path if it's the longest possible delayed path in the circuit. Between any 2 flip-flops at all. And that's what we're looking for. Right? So I look for that longest delay. What else is a factor in the clock speed? Not just the delay of the critical path, but what else matters? Remember? Yeah. Clock skew, yeah, what's clock skew? Right, so I have two flip-flops here, right, and my clock is coming from over here. The clock physically originates from one point in the circuit, right? And it looks like it's going to take a little bit longer for the clock to make it here than it will to this one, right? That's the idea of skew, is that it actually takes time for signals to travel down wires. Not much time, but that could matter. We're dealing with fractions of a second here. Yeah.
The question on that is, so if the clock signal is actually traveling down the wire to everything and all the other signals have to travel through various circuit components, is there ever a time when the clock would arrive at a component after a signal? Because it's traveling pretty much the speed of light down those wires.
After a signal.
So, like, there's just a signal coming, like, into the D and out of the Q on that first flip-flop. Would that signal ever get to the second flip-flop before a clock signal?
Before a clock signal? I don't think so.
So then how wide is the clock signal actually?
The clock itself doesn't matter. It's more the difference between the clocks. The difference between when it arrives here versus when it arrives here that matters. Not necessarily the exact moment that it arrives, but as it relates to the two flip-flops is what actually matters. So it's going to take longer for it to get here, right? The clock cycle that rises here, right, it might actually happen over here at this flip-flop, and that's going to throw all the other timings out of whack. That's what matters. Yeah. What's the, if I examine this path, right, this one that feeds back around into itself, what's the clock skew there? There's none. Yeah, it's 0 because it's talking about itself, right? So there's no difference in the arrival time of the clock at that particular flip-flop because we're talking about the same flip-flop. So clock skew only matters if we are physically talking about two different flip-flops. Okay, so clock skew matters as it relates to clock speed. The delay of my critical path matters. Anything else that matters? There are a couple other things to do. Yeah. Yeah, so I need to make sure that this signal arrives before the setup time of this flip-flop, so I need to make sure the clock signal is long enough to allow for that to happen. Yeah?
I have a question about that. Is do all flip-flops the same size?
No, it depends on how the flip-flops are constructed, what gates it's made out of. We've seen that we can construct flip-flops in various ways, so it depends on a variety of factors.
So which setup time?
The setup time, so yeah, that's a good question. Which setup time am I talking about? The longest? So if this setup time is longer than this setup time, then this matters more. Kind of depends, right? We're talking about, so setup time is the amount of time it has to remain stable before the clock edge, right? So if the signal has to arrive ahead of time by a certain margin, if I'm looking at the destination here, I need to make sure that the delay of this still arrives before the beginning of the setup time for this flip-flop. So the destination flip-flop on my critical path is what matters. The destination setup time matters as it relates to clock speed. The setup time matters in all flip-flops, right? But if we're talking specifically about clock speed, find your critical path, right? It's actually, the critical path is the path with the largest combination of circuit delay due to component logic gates, setup time of the destination flip-flop, and then one other piece. What's that last piece? Propagation delay of this flip-flop, right? How long does it take for the output to actually come out of this flip-flop? What's the cause of propagation delay? We haven't talked about that yet. Where does propagation delay come from in a flip-flop? Yeah. That's this guy. This guy's propagation delay, right? That's what causes propagation delay. So I know this is on the video. It's on the slide that I did in the video. But just to reiterate, since it's a supremely important topic, right? To dictate the clock speed, we need to find the largest combination of propagation delay plus, I guess logic delay. I feel like that's actually supposed to be called something different, but I can't remember right now. This is the delay due to the gates in the critical path plus setup time. Right? This is what dictates the clock. And skew, we talked about skew as well. This is what dictates the clock speed. So find the largest possible combination, right? The largest possible sum of all the different paths between all the different flip-flops. Find the one with the largest value of this, and that dictates your clock speed. Right? Any other questions about that? Do you have a question?
Why is the full-time loss in there? You just can't do not begin the next clock cycle until that.
Why doesn't the hold time matter? So the hold time is the amount of time the signal has to remain stable after the rising edge of the clock cycle, right? But consider I erased my flip-flop. What we're modeling right now is this path out from this guy into this guy, and we want to know, how much time is it going to take so that we don't have a clock cycle that's shorter than that. Hold time happens after this rising edge. So I'm not really concerned about what happens after this fact necessarily. In fact, with the critical path, I know for a fact that it's going to take so long for the signal to traverse that it's probably not going to affect the hold time at all. We do need to be concerned about the hold time. I just don't know that that's a concern with the clock cycle necessarily. Does that make sense? Any other questions before we try some other problems? Okay, let's try some more. Yeah, here we go. This actually is a clock cycle problem, right? So I know it's a wall of text, but it's not that bad. Just a paragraph. Take a few minutes, talk to your neighbors, and then we will go through this problem together in just a few minutes. Yes. So with hold time, you need to worry about setup time. It's always going from we're always talking about so if we're worried about setup time, right? We're worried about so worry about getting your hold time set time
Remember it starts with C.
I think.
Combination. Yeah, is that it?
Oh, because it's gonna copy. Yeah, so if it goes so. Oh, that's after the while.
Yeah. There's something.
No, no, I got it. Yeah.
No, this is like when you're talking
Oh,
about.
yeah, I just don't understand.
From one range to the shortest.
And the whole shortest gap.
There's like, yeah, you need to do more.
If it's different, because the time and space
They have to be stable for some time.
then
Then the clock. Because you need to hold
and then
So the input signal needs to arrive before the setup time. Right? So we're worried about it making it there fast enough. We're also worried about it not changing too soon because it can't lead until after.
Yeah.
So with hold time, we're worried about it changing too fast. With setup time, we're worried about it not getting there fast enough. So they're kind of complementary.
Yeah.
You have to take a look at both extremes.
if it's 15. I was gonna draw it like that. Well,
No, you can.
or, no, it's kind of full time. Even 15 seconds after.
Yeah, sorry, you went.
Well, you couldn't change that.
Yeah, yeah. Yeah. Oh, are you ready for 3 seconds? Yeah, nobody. Yeah.
When you see a problem like this, we're basically looking for a couple things, right? We're looking for setup time violations of hold time. That's basically what we're looking for. Does the signal change during the setup time? Does the signal change during the hold time of either of the flip-flops in question? So, did anybody find a case where setup time and hold time were being violated? We can start working through all the possible combinations, right? So, okay. Is it okay for x to change in time t minus 5? So 5 nanoseconds prior to this change in clock cycle, right? Is it okay for x to change at that point in time? We'll consider what needs to happen. If we look at the maximum possible delay, there's a path from x to a flip-flop that has a maximum possible delay of 7 nanoseconds, right? So it's going to take 7 nanoseconds for that signal x to get to that particular flip-flop, which means that x is not actually going to arrive until over here, right? Is that okay? No, that's not okay at all. We basically blew our setup time out of the water. It's no good for that particular flip-flop. We can't do it. It needs to make it there before the setup time. So that's not acceptable. Can't happen, right? Not okay. What about the other one? You know, there's a path from X to another flip-flop with a minimum delay of 3 nanoseconds. Is that okay? So 3 nanoseconds would get us there at what time? T minus 2, right? 2 nanoseconds before the flip-flop, before the rising edge. Is that okay? That is okay. So, you know, in that case, it's okay for the quick path, but not for the long path. Okay. Doesn't work. For the setup time. Does that make sense? Okay. So we have to take a look at the other cases as well, right? So is it okay for T minus 1? T minus 1 is bad for the same reasons. Actually, that would fail both setup times, right? That would fail both particular setup times. T minus 10. Well, T is horrible for obvious reasons, I hope. T is just no good for obvious reasons. T minus 10 is probably the best case scenario because then I think it arrives in time for both in this particular case. It arrives in time for the set time for both. So we don't have to worry about either flip-flop in that particular case. So mostly a setup time problem. Any questions about that? Questions?
So we're actually looking at what would work to separate the circuit and it not work. We can just fix that problem that would mean that part of the circuit doesn't work with that block.
Now, sure, yeah, absolutely. No, you're right. I guess another way of wording this question, and I believe that I have a different version of this question worded this way, is what if X isn't necessarily an input, but what if X is another flip-flop? That changes things a little bit, right? So in this case, it's worded such as, here's my circuit, right? I basically have 2 flip-flops like this, and X is just an input, right? It takes 7 nanoseconds to get here, it takes 3 nanoseconds to get here, and X is just an input. But what if X is a flip-flop? Well, then that changes things a little bit, right? That changes things. Now here's X. Now I have to worry about not just the making sure that it meets the setup times, but also making sure that it satisfies hold conditions as well. Yeah.
2 questions.
Yeah.
So now, if you were to look at the minimum, maximum clock speed, which would be 9 nanoseconds, because that's the max of the possible propagation delays.
So yeah, so clock skew isn't given, but if we assume it's 0, since it's not given, then it would be maximum possible delay. We also don't have propagation delay of our flip-flops, so again, we assume that it's 0, then yes, it'd be 7 plus 2. Yes.
And then if, like in the ridiculous case where your hold time exceeds the propagation delay plus logic delay plus the set time skew. So in this case, if hold time is like 15 nanoseconds, would then clock speed be decreased to 15 nanoseconds because you then have to
Decrease to 15 nanoseconds. So you're saying if we have a hold time violation because the signal's changing too quickly. Actually, to solve hold time violation, so a hold time violation occurs when a signal is traveling too fast. It makes it to the flip-flop, the change makes it to the flip-flop too quickly, right? It doesn't, it makes it before the end of the hold time window. So the solution to a hold time violation is to insert delay. We actually make that path slower. How do we make a path slower? What do we do? We slow things down. Yeah. Yeah, well, we're using logic gates, so yeah. Just a pair of inverters slow it down, invert it, and then invert it back. There's no logical circuits equivalent, right? And it slows it down by those two inverters. So hold time violations are solved by introducing delay. Typically, a hold time violation will not be, I mean, it can't be in your critical path because it's by definition too fast. Critical paths are really slow. So inserting that delay is not going to affect your clock period, and then your clock period will be able to remain stable. It's a great question. Great question. Any other questions about this before we try some other ones? I've got some other good ones here. Let's take a look at, since we're running out of time, these are great problems, right? I know I'm skipping them, but they're great problems. But I want to take a look at this one. This kind of covers everything. So for the given circuit, are there any hold time violations? What's the smallest possible clock period? if the clock goes from low to high at time t. So we haven't talked about this yet either, right? But the inputs can only change at a particular time. The inputs can only change because they have to match the set of hold time constraints as well, right? So the inputs have to match those constraints. So when must they remain stable in relation to the clock period? And then when will the output y change? The delays for everything are given down here. I know the text is a little bit small. I can see if I can blow this up a little bit so that you can read it a little bit better. But all the delays for everything are given down here. Minimum and maximum delays for the flip-flops as well as the logic gates, right? Hold time, setup time for the flip-flops, and then the clock skew from these two to those, from that flip-flop to the other two flip-flops. So take a few minutes. This should wrap it up for us. And we'll discuss this answer in about 8 minutes. Contamination. I've never heard that term, actually. Contamination. Sounds like a zombie virus. Just for data activities. So in my experience, with the right process, like quick changing, just got out of order. It doesn't accept it. So it's basically just ignoring anything that tries to do lots. Does that make sense? I think that's kind of what the reflection is. Just basically say, I'm busy right now. I'm resetting myself. I don't care what you try to do to me. I'm just going to go back and reset myself. No, I don't think. You certainly could. I don't think it needs to be that complicated. I think you can just redirect it. For anything, for any combination. We're basically saying I don't care what happens after this. I'm just going to go back to no, I didn't say anything about this. I think the answer is I realize you're trying to change one folder to the nickels, but I'm just going to go back to
Oh, I know. I did it.
what do you indicate?
or at least,
When you say it wants to use 1 nanosecond, you're saying it's 1 nanosecond. It's going to take 1 nanosecond longer for it to make it here and here. Okay, just not keeping it. No, it's not like 1 and then 2. No.
I didn't intend it to be that way.
No.
Yeah, that part is a little ambiguous. Okay, we are running out of time, so let's start trying to get through as much of this as we can in the last 5 minutes or so. Anybody find any hold time violations? Are there any hold time violations? What am I looking for in terms of hold time violations? In this case, it's actually pretty easy to determine if there aren't any hold time violations. We see that the hold time here is 1 nanosecond. We also see that the minimum possible delay for a gate is 1 nanosecond. Right? So this gate here, this is the shortest path, right? Hold time, we're worried about things getting there too fast. So I don't care about this so much. Right? If there's a hold time violation here, then there's definitely going to be a hold time violation here. So let's take a look at the shortest path for hold time violations. I'm going to look at the quickest possible route for hold time violations. So I know it's going to take 1 nanosecond just to get out of the flip-flop, and another nanosecond just to get through this logic gate here, minimum, right? And so that's 2 nanoseconds. Even if I take the clock skew into account, that's still going to be okay in terms of hold time. There is no way, there's no possible way that the signal can get from here to here before the end of the hold time. Does that make sense, everybody? So the equation is the minimum propagation delay plus the minimum propagation through a logic gate minus the clock skew. So that's 1 plus 1 is 2 minus 1, right, is 1. Has to be greater than or equal to the whole time, which is 1. In this case, they're equal. That's okay. I'm not even going to bother to check this one because I know the delay is much longer than this one, so I'm not worried about whole time violations. Whole time is signals moving too fast. Yes?
Will manufacture a hold time violation though by putting a picosecond pulse delay?
Putting a picosecond pulse into A.
Like if you set root true, or just really anywhere, just doing a very quick pulse as an impulse, as an input.
Well, that pulse would have to time up with the rising edge of the clock.
Yeah.
At the very least. I mean, so A, B, and C are a different question. In fact, they have a literally different question for that particular piece. And the whole time does matter. You're absolutely correct as it relates to the inputs. But that does not relate to the path between flip-flops at all. I see where you're getting at. We're going to answer that question in just a minute. Any other questions? Okay, so for hold time violations, we're looking for the shortest possible path between flip-flops, the quickest possible path. For the possible clock period, we're looking for the largest possible path, the critical path, right? I think it's fairly obvious that this is the critical path in this case. So we want to take the largest possible value of everything. So the largest propagation delay from here, that's 3 nanoseconds. The largest gate delay for these 3 gates, that's another 4 apiece, so we're at 15 nanoseconds, right? Plus the setup time, which is 2 nanoseconds, plus the clock speed, which is 1 nanosecond, so that puts us at what, 18 nanoseconds? Is that right? For our clock period. And now we can talk about the inputs. If we have, a rising edge of the clock at time t, so here's my clock, here's time t, right? And I see that rising edge. I want to know when it's safe to change A and when it's safe to change C. So again, I have to worry about both setup and hold time here. It's not just one or the other, it's actually both. So setup time, I'm now worried about A changing during that setup window. So am I worried about A making it through here very quickly, or A taking its sweet time and going through here very slowly? Which matters? I'm worrying about setup time violations for A. I'm worried about fast or slow. Fast. I'm worried about this changing too quickly, right? So I'm going to use the minimum propagation delay for each of these, which is 1 nanosecond. And I'm worried about the setup time as well, which is 2 nanoseconds. Which means that if the clock changes at time t, the value of A has to remain stable beginning at t minus 5 nanoseconds. It can change before this point, but after this point, it has to remain stable for a certain period of time, right? That's for A. So when can it change again? At what point can it change again? Well, that depends on the hold time. So for the hold time, right? Yes. Did I mess something up? Let me think about it. It's a good question. Let's make sure that we have it right. Why are we worried about minimum delay instead of maximum? So if I use maximum delay, that would be 3, 6. Or I'm sorry, that's 4, 8, 12 plus the setup time would be 14 nanoseconds. So A could not change from 14 nanoseconds. Is that right, though? A could not change from 14 nanoseconds in. That's not correct. We're worried about a change in A making it through very quickly during the setup. So here's my setup window, right? 2 nanoseconds. Right? 2 nanoseconds. So we're worried about changing A such that it disrupts this particular speed. So I guess, hang on. I should have brought the equations with me. They're in the slides. Let me just look them up in the slides real quickly. I know we're running short on time. We're not going to get this finished. But I do want to make sure to get this part right. So let's just look it up and make sure we get it right. Input timing analysis. All right, fantastic. Clock edge minus maximum. All right, so I did have it wrong. Thank you for asking. Minus the maximum input to flip-flop delay plus the setup time. So that would indicate that it would be 12 plus 2 is t minus 14. I did that wrong. My apologies. My apologies. The end of this timing period depends on the hold time, so I want to make sure not to violate the setup time constraints as well as the hold time constraints. Right? So for the end of this period, we take a look at the clock edge plus the hold time minus the minimum input flip-flop delay, which would be t plus 4, right? The hold time is 1 minus that would actually be t minus 2. So A cannot change from t minus 14 to t minus 2. Thank you for bringing that up. That actually makes sense, right? That actually makes sense in a way. if I change A in between this period, I really run the risk of violating the setup time. Towards the beginning of this, I run the risk of violating the setup time. If I change it towards the end of this period, I run the risk of violating the hold time. We're out of time for now. We'll do a couple more of these on Thursday. I'll see you guys then.
So I was wondering why sometimes you can put when statements in a process, but then sometimes it doesn't.
Sometimes